let's investigate this somewhat funky limit. What we're doing is we're taking the limit as our x goes to 0 from the right, that's what the plus denotes, of sine of 1 over x. So I want to figure out, what does the graph of sine of 1 over x actually look like? Okay, so let me think first about what the sine of x looks like just itself. Sine of x, you might recall, goes up and down and up and down, something like this, and it obeys this pattern forever. It keeps going up and down and up and down and up and down. So if I look at sine of 1 over x now, well, sine of 1 over x, and I'm taking numbers that are really close to 0. So 1 over a number really close to 0 is a really large number. Like, for example, if I take 0.01, then 1 over 0.01 is 100. So as these numbers x get closer and closer and closer to 0, what's inside of the sine gets really, really, really big. But if I think about what happens as sine gets really, really big, sine of x itself, not sine of 1 over x, as sine of x goes really big, well, it just keeps going up and down and up and down and up and down between -1 and 1. So I think the graph is going to look a little something like this. Kind of bizarre, but this is the graph of sine of 1 over x. And the idea here is that in this region where you see it starts oscillating really, 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 really quickly, that's because in a tiny small interval around 0 from the right, that what you're inputting is these bigger and bigger and bigger numbers, a million, a billion, a trillion, and sine of a million, sine of a billion, sine of a trillion, these are going to be oscillating between -1 and 1 really, really quickly. And so we get the same oscillation between -1 and 1, but it's sort of compressed when you do sine of 1 over x instead. Okay, well, now that we have what the graph of this thing looks like, what is the limit actually? As in, if I go right to 0 here, and I'm coming to it from the right, well, we never approach any one value. If I'm around 0, sometimes I'm up here at 1, sometimes I'm down here at -1, sometimes I'm somewhere in the middle. There's no single value, whereas I get closer to 0 from the right, that this approaches it. It just oscillates sort of infinitely fast as I start going towards 0 from the right. So this is a sort of a funky function, and we're going to say that this limit does not exist, or in other words, DNE. Now we're going to investigate a very slightly different limit. We're still taking the limit as x goes to 0 from the right, and we still have the function sine of 1 over x, but now we have this extra factor multiplied by x. And the difference here is that as x goes to 0, the function that's just x, it clearly goes to 0 as well. So while the sine of 1 over x oscillated between the -1 and the 1, and it sort of did that going faster and faster and faster as we went towards 0 from the right, it's now being multiplied by this other factor x that drags it down to 0. So the graph is going to look like this. X sine 1 over x, it comes in and it wants to do that same oscillation, but it's bounded by this graph of x. And what I've put here in these blue, I call them envelope functions. And what we have is one function which is just x, and another function which is minus x. And then because sine of 1 over x always is between +1 and -1, then x times sine of 1 over x is always between x and minus x. So that's why I draw this graph of x and this graph of minus x. They're my envelope functions. And then this x sine 1 over x, it does this sort of oscillatory behavior that it wants to do, but it's bounded between this. So now if I look at what the limit's going to be, this looks like it's getting closer and closer and closer to 0, and I think I can say that the limit is 0. And so I'm going to say that the limit as x goes to 0 from the right of x sine of 1 over x is just going to be equal to 0. Now, the basic logic that we've used in this particular example, I can extrapolate into its own theorem. So the way the squeeze theorem works is that you have three different functions, f, g, and h. And that the f is the smaller function, the h is the bigger function, and in the middle between the two is this function g, and that g is bounded on the two sides by the f and the h, and we care about this g. We want to know what is the limit as we get close to some a of that g. And then what happens is that if the limit of the smaller function and the limit of the bigger function, if they are both going to be equal to some number L, then this function g in the middle is squeezed between them and must also have the same limit of L. So in the previous case, it was the x sine 1 over x that we were interested in, and that we were bounding it between the positive x and the minus x, and that both of those limits, the limits as x and the limit of minus x, both of those went to 0 as x went to 0 from the right. And so that the limit of the function we were actually interested in, the x sine of 1 over x, that it was forced to 0 as well. If we want to see this example algebraically, you might begin in this way. You might observe that minus 1 is always between sine of 1 over x, and sine of 1 over x is always going to be less than 1 as well. That this is one of the fundamental bounds on the function sine. And then if this is true, I could then come and say that minus x is always smaller than x sine of 1 over x, and that's going to be smaller than x in the domain where our x is going to be greater than 0. And then applying the theorem, we have our smaller function f here, we have our bigger function h here. We know that the limit as x goes to 0 from the right of both x and the limit as x goes to 0 from the right of the function minus x, both of those are going to be equal to 0. And finally, that allows us to deduce that the limit as x goes to 0 from the right of the big function, the x sine of 1 over x, that is equal to 0 by the squeeze theorem, because we have these squeezed limits being the same thing, and we know that what we're interested in is between these other two functions, so it must be forced to 0 as well.